This video is about our paper, Dynamic Local Regret for Non-Convex Online Forecasting, presented at NeurIPS 2019. Forecasting is the task of predicting future outcomes based on previous observations. There are many applications for forecasting, including financial market analysis, inventory planning, weather prediction, and earthquake forecasting. Consider a forecasting model where you pre-train a model using the available dataset. Let's call this an initial model. As you observe new dataset, you keep using this model. However, this approach might lead to inaccurate forecasting if concept drift occurs. In other words, if the relationship between the input and the outputs of the model changes over time. Ideally, we should update the model as you observe new, fresh dataset. There are two ways to keep our forecasting model up to date. We can either retrain the model from scratch using the entire dataset, which can be computationally expensive and time-consuming, especially if the model is complex. Or we can update the model based on the initial model by just using the new dataset, which is called online learning. The performance of online learning algorithms is measured by regret, which is the difference between cumulative loss and the minimum loss. This definition of standard regret is not appropriate for non-convex models due to NP hardness. Since the state-of-the-art forecasting models are non-convex deep learning models, it's necessary to have a regret that's appropriate for non-convex models. Hazan et al. Introduced a notion of local regret where the main idea is averaging the gradients of the most recent loss functions within a sliding window that are evaluated at the current parameter. This approach addresses the non-convexity. However, since it assumes a static best model, it's not appropriate for dynamic environments. We introduced dynamic local regret, which addresses both non-convexity and dynamic environment. Similar to the local regret, we use a sliding window to compute gradients, but we compute each loss at their corresponding parameter, and we introduce an exponential term alpha, which assigns more weight to the most recent losses. We introduced an update rule called dynamic exponential time smoothed SGD as an online learning algorithm. We show that our update rule guarantees sublinear convergence according to our dynamic local regret. In our experimental results on publicly available time series dataset, we show that our approach has two main advantages over the alternatives. First, our update is less sensitive to the hyperparameters, and second, it is more computationally efficient. Thank you for your attention, and please check our paper for details.